Just as in building a house, after the foundation is poured, we then need to work on the structure. There are 3 sessions in this videotape which address this point. In session 4, we will look into layout and process improvement in order to establish a streamlined flow in the factory. In session 5, we will study different tools which function as a nervous system in the factory and allow us to quickly respond when something starts to go wrong. In session 6, we will address the necessary skills for problem solving, especially in the areas of quality and machine maintenance. One of the most important concepts to learn for making a factory competitive is flow production. Here, flow refers to the movement of material through the plant. It assumes that material will not be stagnant at any point in time from the receiving of raw material to the shipping of finished goods. The benefit of flow production are early detection of problems, quick delivery of products to customers, lower inventories, flexibility to respond to customer demands quickly, and a more organized workplace. Contrasting to this, we have disturbed flow in our factory, making the situation almost uncontrollable in some cases. Materials may be accumulated at excessive inventories, or we can't produce product because of a shortage of parts. In order to achieve production flow, however, there is also a long list of hurdles to clear. Even though the list of hurdles is long, it's important for each of us to believe that there is always a way to progress further. Instead of thinking of these hurdles as insurmountable obstacles, we need to think positively in terms of flow production being possible. Parts can come on time. Machines can run as required. We can produce quality products. And we can solve problems as they arise. In other words, man, machine, material, and method, the 4 major elements of production, are working together to achieve flow production. In discussing many problems to overcome in developing flow production, let us first focus on layout. When describing layouts, there are 2 major types. A process-oriented layout is one where machines are located according to their function, whereas a product-oriented layout is one where machines are laid out according to the flow of materials. Not surprisingly, a product-oriented layout is much more suitable for achieving flow production. As we develop a product-oriented layout to achieve flow production, the material transfer between different processes becomes much easier. Also, production lead times and inventories accumulated between processes will be reduced significantly. Take the case of Fairplace Manufacturers Incorporated. You can see the change in material flow. Before, the flow was very complex. Now there are 4 major flows. 1 for fireplaces, 1 for glass doors, 1 for pipes, and 1 for accessories. Each is dedicated by product line, more like a factory within a factory. Because of the product focus, this is sometimes referred to as focus factory arrangement. Now, raw materials are delivered to the point of use, and material flow is greatly simplified. New layout is easier to manage, and the benefits achieved were substantial.
It seems like what you have just explained to me was simply to tie different operations together based on the material flow. Am I right?
Yes.
Then what's so difficult about doing it? It seems so natural.
You're right, but often we put the same type of machines together rather than think about the flow of material. Also, we may simply put machines where there is open space. We may even put or buy the wrong kind of machines.
What do you mean by that?
See this example. You see, it's difficult to streamline the flow in the case on the left. But if you can dedicate a machine to material flow, as you see on the right, it is easy to develop a streamlined flow.
Well, that means we'll have to have more machines.
Yes, but more compact or smaller machines.
But still, that may be expensive.
Possibly, but you should be able to utilize people better, keep inventory lower, shorten production lead times, and increase the quality levels because this is easy to manage.
I see. So we have to look at the total picture. Is that what you're saying?
Yes. Let's take a look at a few examples here.
We run lot sizes of about 500 pieces of each casting to each individual machine. And we start up running through one of the millers up in this area. We then send them down to do all the drilling and the tapping, which is an area down in the drill room, which is the other end of the shop. And after that, they would go through the cleaning process, come through inspection, and then going to the warehouse. And following the warehouse, they pull out whenever they needed to go into assembly. Now, to give some statistics as to how long all this used to take was, for average lot size of 500 pieces, it used to take anywhere between 10 and 15 days to go through the whole shop. From a quality point of view, we'd have rejection percentages of around 20% for each item. From a cost point of view, if I relate cost to just direct labor right now, this part used to take about 7 minutes to produce, this part used to take about 5 minutes to produce. Now that we've set up the cell, what we've done is brought all the machines that are involved in the process to one area. So we have turning process, the drawing and tapping process. All the machines are compressed together, and we have one operator operating the whole cell. Now the effect of this is that, first of all, we reduced down all the travel time throughout the whole shop. We can get one part going through each machine, going from start to finish in a very, very short time. And in fact, what we've done the lead time is we compressed the lead time from our 10 to 15 days down to, in effect, 3 minutes.
In addition to lead time, reject rate went down from 20% to 2%, and the operator's work time per part was cut in half. Plus, since a part goes through the whole cell in only 3 minutes, there's no need for a computer system to track it. Production control is now in the hands of the operator. In this example, 4 operations were previously run independently of each other. When all 4 operations were combined, the cart full of inventories going between these operations were eliminated. This arrangement also pointed out which operation needed further improvement. For example, there was still sizable inventory buildup between each operation. The parts are not yet moving through like a stream, indicating further improvement potential, not a problem or an impasse. Also in the future, these 4 operations may be tied to the assembly line, thus furthering the integration of material flow. This is an example of semiconductor fabrication. The need for the 3rd clean room was limited by simply rearranging the machines, integrating the 3 rooms into 2, thus helping smooth material flow.
The results have been quite dramatic. The racks are empty, the material is moving, the amount of material we needed in the line has been reduced by a factor of 2. This reduction has allowed us to increase our capacity to have an empty room, a room we could bring new equipment for other new things that we want to do in our technology.
This example will illustrate the benefits of a product-oriented layout. First, this represents the typical process-oriented layout. Here, completing the first batch of 5 units takes a fair amount of time. Our next example represents the product-oriented layout. Now, to complete the same batch of 5 units takes much less time, and work in process is substantially reduced when compared to the previous layout. This is the ideal. When this is accomplished, this is called one-piece flow production. The U-shaped line, or U-shaped cell, as it may be called, has unique features which help to achieve this one-piece flow production. A U-shaped line can achieve improved communication within the U-shaped line, simpler flow and easier production control, ease in combined work steps, more flexibility for changing production volume simply by changing the number of people in the line, and better teamwork between and increased ownership for operators in achieving common goals. Now let's hear from some people who were involved in converting to these new layouts.
In our old production layout, you can see we were organized along production process cells. We had a sub-assembly area feeding into a higher level of assembly, feeding into a higher level of assembly, and so on until the product made through the production process. In this chart, you can see the black dots representing people and how they were placed. And there were many barriers to the movement of materials and the communications just because of the layout. You can also see the production process with these green arrows as being fairly awkward and not as smooth as it could have been. To contrast that, we can look at our current layout. In this case, what you see is we've eliminated roughly 25% of our production operation floor space and introduced U-shaped production lines that are responsible to the complete assembly. You can see the black dots again representing people in the production line, and the production flow has been greatly streamlined. The barrier to production that exists in the old layout no longer exists. There's a great deal of openness in the work cells. Information is easily gathered and shared amongst individuals. The feedback of problems from the person at the end of the line to the beginning of the line, if there's a problem, is very fast. And also, there's a great deal of personal identification that happens within this team of people. They're able to recognize the goal, the end being a common goal, and they can share and help each other a great deal.
Where we've come from is quite an improvement. In the old days, we still managed to produce units, but we always had the traditional end-of-the-month crunch, where we were scheduled to produce a certain number of units. At the end of the month, we would produce them, but it was the last 3 days of the month. And we had a lot of confusion online, to be honest. As stated before, product flow wasn't quite organized. People were building to standard, yet were not being consumed that way. And what we've got now is a very precise movement, and it eliminates the end-of-the-month crunch specifically. It's created very linear flow throughout the organization on through shipping, which in turn helps support the customer, does support the customer.
The very first cell we produced was a cell that produced these little four-way valves for Newcon, and for 13 years the very best time we could assemble these in was 7 minutes. After our first cell was developed, we produced this valve in 3.5 minutes, which cut that assembly time in half. Not only do you save time and energy in building the product, but you end up with a better product. You end up with a product that's brand new, that hasn't been in inventory, and is the latest drawing. It's important to remember that a cell's never finished. You can get it to a certain point, but there's always time for improvement. And most of those improvements are going to come through the people who are working the cell. They realize where their wasted movements are, where their movements are going, and they realize they can tell you just little ideas like we need a tool here, or we need to move this bench a little bit to the left. And to pay real close attention with developing cells is to the fine points of where the product should be set down or movements that you're doing that you feel are wasted.
We thought that it would be very good to start with a simple part. This is an idler gear that goes in our 5-speed transmission. The cell that we worked on is simply a cell that hobbed these teeth, and then we do the tooth pointing in another operation, and then we do a finishing operation. Here's how this cell was laid out originally. This was typical of the inline kind of processing we've had for many, many years here at BorgWarner. And it's what we've done, the plant layout, everywhere there was inventory, we colored that in red. The incoming stock came in here in tote boxes, big 4-foot cube boxes. There was an operator stationed here that did the hopping operation, and then he stored them on a, we call these Lazy Susans. They're about 4 feet in diameter with several layers, so you could put a lot of parts on those. And there was another operator stationed here that did the tooth pointing operation that I mentioned. And then again, the operator stored them on another Lazy Susan. The last cell then consisted of 2 of these shaving machines, and then we filled this conveyor full of conveyor racks, and finally washed the parts and put them in another cargo tanker where they went to heat treat. Our U-shaped concept was taking all that same equipment and arranging it in a U-shaped line. Here we're showing the incoming stock right here, and an operator picks a part up, and he hubs it, chamfers it, does a deburring operation, which is down here, and then shaves it, washes it, and puts it in an outgoing tote box. So you can see readily we had 3 operators working here, and we were able to run this cell with 2 operators, and they sort of chase each other around that cell in a merry-go-round fashion.
By spending a few $1,000s to change the machine locations, more than $100,000 a year was saved with productivity improvements.
This is the complete gear cutting department for our T5 transmission. And you can see that these were all progressive lines, lots of roller conveyor, and lots of these infamous Lazy Susans. And wherever you see those round circles or these long spans of conveyor, that was inventory. So after we've gone through this department and completed our JIT, this is what it looks like. You can see all floor space has been freed up for other product, and you see no conveyors or Lazy Susans. Lines are in JIT form, U-shaped, and we're very proud of what we've accomplished. But the key thing I think we learned in doing this is when we made the first U-shaped line that I described in detail, we did that without any operator involvement. It was just a matter of the industrial engineers went out there and over the weekend we rearranged the equipment. When the people came in on Monday morning, here was a new operation for them to run. So there was a lot of resentment naturally from that.
So I think many times engineers need to talk to us a little bit more about how we work and then how they can plan the area better with their ideas and our ideas so that we can work together. It's just like, say, if I were going to go to your desk and rearrange all the papers on your desk or put the telephone down on the floor. It's like someone coming in and doing that. So I really believe that we can work better with the engineers and other planners if we would get together as in a team.
So we went through a lot of pain and suffering and getting that cycle back up to speed. So in the second cell that we arranged, we corrected that problem. We got all the people in the room, showed them what we intended to do, give them a copy of the plant layout, and asked them if they wanted to change the layout, what would they recommend? Well, as it turned out, they didn't recommend anything, but the smoothness of the startup of that was the difference of day and night. So any other cells that we've done have been done with total operator involvement, and that's the key to making this thing work. People are anxious to correct those deadly wastes of bad quality, lots of inventory, and not utilizing their skills, but trying to utilize the machine. So I guess if there was any recommendation I would make, it's to get operators involved if you're going to attain this kind of success.
The key point is that in order to achieve the full benefits of a U-shaped line, we need to involve operators and enhance our overall skills.
The reason why I think it's a very good job and I think it's a good cycle is because we take a raw piece of stock and we run it from beginning to end. And while we're in the process, we're able to make any adjustments or any alterations that are necessary. Okay, whereas before, maybe they may have one person doing the semi-finish cut, then slide on down the line, okay, and maybe they wouldn't be able to catch anything that is wrong. I feel like with the AI cycle and the way it's set up, we'll be able to catch anything that goes wrong.
Since there is less inventory on line, with more value-added work for the operator to do, U-shaped line arrangement requires that operator develop a new set of skills. These skills include understanding a wider scope of their work, working on a broader range of machines or procedures, working as a team instead of as individuals, addressing problems quickly as they arise, and gaining ownership of running the line without much supervision. Industrial engineers are not the only ones who can develop layouts. In this case, an operator developed a U-shaped assembly line with flow production concept, where operators complete the assembly from start to finish. This resulted in a major reduction of inventory, floor space, and production lead time. This is an example of a line developed by Aisin Seikei, a Pearl division in Japan. In this example, there are 8 operators running 23 machines to produce one product. This line has 7 machines, but there are just 2 operators. Each operator handles 3 machines, and sometimes more. Called multi-machine handling, this is a very common practice in Japan. In a conventional line, one operator is responsible for 10 one machine. As a result, in-process inventory tends to pile up as machine speed increases and quality becomes more inconsistent. But in the line shown, the machines may be running slower than typical machine speeds, which is fine, as long as they meet the customer's need and have finished sewing the material prior to the operator's time. That is, the time from when the work is ready to when the operator returns from performing another task. In such situations, compact, unsophisticated, and relatively inexpensive machines are desirable, as they can often deliver high quality with fewer problems. Machines are modified for simplicity's sake, so that even new employee can be put right to the line. Because the machine is so easy to handle, operator training on each machine is extremely quick. Thus, each operator quickly becomes multifunctional. In integrated lines such as this, any interruption, even as minor as changing a thread bobbin, will cause imbalances. To minimize this, a mutual help zone is provided, allowing the work to be passed on, sort of like the takeover zone of relay race. This evens out the work performed by the operators and ensures smooth production flow. This operator at Japanese automobile manufacturer Kanto Auto Works is practicing one-piece flow production. The machines are laid out to accommodate this flow, allowing 2 different parts to be produced on this line. As the layout shows, the operator does 15 steps for one part and 10 steps for the other, for a total of 25 steps to complete the cycle. A good example of multi-process handling. In this arrangement, there are 4 operators, each following the other. Because of the practice, as market demands change, the number of operators can be changed accordingly. Notice the high level of housekeeping and workplace organization shown here. Notice also the simple mechanism used to eject a part, as well as the automatic parts transfer system. Not sophisticated or expensive, but they work. So the benefits of this type of layout include increased productivity, increased flexibility to changes in market demands, increased quality, and increased operator morale. Again, however, people are the key to making this type of arrangement a real success. Only when we begin to understand the potential of these techniques and the importance of people involved in implementing them will we be able to figure out how to use the freed up labor time. The point being that our organization should allow its people to grow, to acquire more skills, and to share in benefits through secure employment. Without the involvement of the people, we will never be able to achieve continuous improvement.
I think I understand the potential of these improvements, but can you show me an example of this improvement process?
Okay, here's an example. This is a company that makes automotive switches. This layout was developed before the change. As you can see, the material flow was very complex.
Wow.
Now, this is the new layout. It is U-shaped, very simple flow.
Oh, amazing.
The result was reduction of inventory, labor saving, less confusion of work, and total time to process the material was reduced from 3 days to 17 minutes.
Wait a minute, it was reduced from 3 days to 17 minutes?
Right. In fact, after the change was successfully completed, they celebrated with a couple of balloons.
That is wonderful. But are the benefits always this impressive?
Generally speaking, you may be able to increase productivity by 30 to 40%, and reduce floor space also by 30 to, I would say, 40% or sometimes 50%, and significantly reduce the inventory while making major improvements in production lead time, often again from days or weeks to even minutes.
these are major improvements. But what about people? I mean, those who are removed from the previous job.
This is a very critical question. What I have found most effective, though, is when there is excessive labor, remove the ones with the most skills, have him or her do more advanced jobs. This in turn should generate more business for the company. And all layoffs should result from improvement activities. If a company lays off people because of their improvement activities, I don't think such a company can continue improvement for a very long time.
What about machine breakdown? If any machine goes down, you're going to be big trouble, right?
Yes, but you should improve the maintenance activity too. That's how we can move forward.
It sounds like there are a lot of changes associated with this type of improvement.
Yes, but by focusing your efforts and carefully planning the move, you'll be able to gain confidence as you go and share benefit with all involved.
I understand.
At Puritan Bennett, this is what they recommend to those not yet utilizing these techniques.
Take the time. We were as skeptical as all our organizations when we first started, but it seemed that once you start with the just-in-time approach, it just catapults. You make one improvement after the next, and pretty soon you've got a major improvement that you really see in both time and labor. And morale. The morale is really boosted. You take a group of people and put them together, and once you got them working together as a team, you've got a tremendous asset to your company.
Even if layout and operator skills are improved, further gains will not be achieved without a reliable system for monitoring the operation. Also, we need to provide adequate feedback to people. Quick detection of problems is critically important for taking corrective action in a timely manner. In this session, we'll study the means of providing better monitoring and feedback in our daily operations so that a production system can become autonomously controlled. Jidoka, or automation, is a concept developed in Japan to provide machines with the autonomous capability to use judgment. Without this concept, a machine may move by itself, but it may not be working for you. By using Jidoka, operators can be away or separated from the machine operation, and thus their time can be better utilized. Also, more rapid troubleshooting is possible since problems are discovered on the spot. Making this work, however, requires a great deal of discipline. Whenever a process is disturbed, we need to identify the problem by first stopping production. Then we resolve the problem, and finally regain the streamlined flow as quickly as possible. Otherwise, the same problem may haunt us forever. The Jidoka concept applies not only to machine operations, but also to line operations. This is accomplished with line stop buttons by the operator, where he or she will push the button to get supervisor's assistance when a problem arises. This concept is called line stop concept, and is a variation of Jidoka. By stopping the line, we expose any problems, prevent the production of quality products on time, so that we can take corrective action as early as possible. If a line has repetitive problems causing frequent line stops, these will only be fixed by focusing people's efforts. Therefore, we need to develop an effective nervous system in our factory in order to expose the waste and take corrective action. Jidoka, in its broadest sense, is therefore a concept for exposing problems and taking corrective actions autonomously. To do this effectively, there are several techniques that we can use in developing an effective nervous system. They are Anbone, Poka-yoke, and visual control. Anbone means lantern in Japanese, just as the lantern may guide people walking in the dark, and Andon light helps expose abnormal conditions in the factory. In other words, Andon or trouble light will help abnormal conditions become obvious enough to catch people's attention. Buzzers, and in some cases video cameras, also facilitate communication without delay. When factory operations are linked by these means, the factory will function similarly to our reflexive muscle system. Just as our muscles will pull our hand away if we were to touch a hot plate, corrective action should be taken immediately. This Andon board from Japanese automotive facility is a typical example. As the light goes on, there may also be music coming out of a loudspeaker. This too may be specific to a line, so that people won't be confused if there are several lines in the same neighborhood. The next example is a part delivery Andon. As parts run low, the operator pushes the button that informs the material handler or tracker of his need. This signal is then displayed at the Andon board, signaling the tracker to deliver the parts requested by the operator. This helps keep communication smooth and line-side inventory low. Parts are delivered only when required, not too early, not too late. Another example of this reflective muscle system is called Poka-yoke. Poka-yoke is a Japanese word that translates as foolproof or fail-safe mechanism. Poka-yoke helps make the operator's work easier, and at the same time, it eliminates the troubles associated with defects, safety, and mistakes in operation without requiring any undue attention of the operators. There are many different examples of Poka-yoke. This particular example is from Borg Warner. As a U-shaped line was being developed, the employees came up with Poka-yoke so that they could run multiple machines without confusion.
Another problem we encountered was the fact that now an operator had to have more skills. He had to run 3 different kinds of operations rather than just one. And so in doing that, it's easy for an operator to get confused and to load a part backwards and possibly wreck it. And we had that problem on our hobby machines. And this is the little idle gear that I've shown you, shown here in yellow. And there's a problem with that part. If you load it on the machine backwards, then the teeth are on this side rather than on that side. So when the tool slide comes in on Rapid Traverse, we would break this cutting tool. And those cutting tools come at about $1,000 a piece. So we came up with the idea to Poka-yoke this so that the operator physically cannot load the machine and start it if he loads backwards. And all we did was, shown in red here is a little collar that slips over the arbor, and it has some little projections on it that go over that flange. So if the operator puts the part on backwards, then this flange will stick out in this area, and then the clamping mechanism here on the end will not clamp. So you cannot load the machine backwards and therefore break the tool.
This is an example of Poka-yoke for the welding shop of a Japanese automotive parts manufacturer. Since many welds were required in this assembly operation, sometimes a weld was skipped. This happened a few times a month, causing complaints from the customer. However, an idea was generated to make a gate, and only when all processes were completed would an electrical signal open the gate up. Since this gate didn't open if a step was missed, this type of mistake was totally eliminated. This is an example from a compressor assembly line of Japanese manufacturer Mitsubishi Electric. In this operation, the operator puts oil into the compressor. Since you can't see from the outside whether oil had been put in or not, mistakes were made. Sometimes too much oil was put in, sometimes none at all. The idea was developed to put in a gate that only opens after the right amount of oil had been put in the compressor. The gate opening notifies the operator that he or she need not be concerned with the oil level. This is an assembly line in the household goods division of Japanese manufacturer Aisin Seiki. In this line, different parts are used for different models of their product. Since mixed production requires more frequent and faster model changeovers than a conventional line, people came up with the idea of using a light indicator to distinguish the different models as a reminder for the operators. If we compare these previous examples to this example, where incoming inspection is taking place to check the parts from suppliers, we should understand the benefit of practicing quality at the source. In principle, the people who are providing parts should be responsible for their quality, delivery, and cost for the customers. This provides quick detection and correction of problems, while the other is a very slow process. As these examples of line stop, Andon, and Poka-yoke demonstrate, the Jidoka concept can be used to develop an autonomous control system. If we use visual aids to practice this communication and control, we call this visual control. As the need arises and is benefited visually, we take action. However, it requires a great deal of trust and discipline among people involved for the system to function properly. If we expand this notion of autonomous control, the Jidoka concept may include the display of charts describing the key indexes, production control boards comparing the scheduled production with the actual, posting pictures from around the factory to address housekeeping efforts, improvement boards explaining before and after situations for people to learn how improvements were achieved, and even yellow lines on the floor showing where to store parts can become part of this monitoring and feedback system. As Jidoka and visual control will increase communication, plant newspapers and photos can also help promote better communication.
We tried to do different things. We tried to make it more like a family. And what we tried to do is get good communication between the different shifts and between different areas that they were. And one of the ways we've been doing this is through this monthly or so newsletter. And in fact, it's called In Focus. What we do is try to get input from the owner-operators as well, the engineers and manufacturing managers and production control and everybody, just to get little 2 or 3 sentence news items that people would be interested in. When machines are going to get moved, when things are going to be realigned, when there's cost reductions, they found a cheap way to do this, or part changes, or just a lot of different information. So we try to have at least a couple pictures in at each time. Nothing too professional. We just take Polaroid pictures, copy them on to plain copier, 2-sided copies, do it on my PC with a word processing package. Not fancy, but it works. And it's interesting because sometimes it doesn't seem like everyone is reading it. But last month there was an article in there about we these needle bearings that we have to tear down when we have to repair a unit. The needle bearings grease all over them, and in the past we've kind of been going back and forth trying to figure out whether it's cost effective to wash the grease off or just to throw them out. Finally, an engineer looked into it and came up with a method and found out it was not going to be cost effective. So we said, okay, this is the answer. It's not going to be cost effective. We're not going to do this. Just throw them out. And 2 different people came in to me and said, wait a minute, the process, was it this, was it this? And both of those people then talked to the engineer that looked into it and told them about these more cost-effective methods, and we now are washing wheel bearings and reusing them, and it's saving money because people heard about this and it sparked interest. Another thing is we take pictures of just operators working or taking a break or whatever. We try to get all 3 shifts, and we post these pictures on the board, them out near the door where you go out, and as the pictures go up, it's amazing. There's crowds that gather. People will really notice when new pictures are up, and they come and they look and want to see if they're on there, or any of their friends are on there, or how they looked in the pictures, or what they're doing, and is their air clean in the pictures, or is they having a housekeeping problem? And it's interesting. Sometimes they take pictures, but they like it, and they look forward to it. And sometimes they write funny captions on the bottom. Nothing negative, just humorous, and people like that.
In effect, these are forms of just-in-time information transfer inside the factory. You might contrast these examples of visual control with using a computer for collecting, processing, and distributing data. Even though the computer has its own important place in manufacturing, those using visual control may be quick to point out that you do not need a computer to tell you whether a box is empty or full. In summary, practicing visual control and Jidoka can be compared to nervous and muscular systems in the human body, which can respond readily to environmental changes. The point is to develop a self-controlled system. As mentioned before, however, accomplishing this requires the involvement of everyone.
I like the analogy of the nervous system and information system, plus the simple means of communication. But does this mean you are against the use of computers?
Not necessarily. Like anything else, if we do not have an adequate ability to use them, we may find them producing or storing a lot of waste.
Aha! So what you are saying is we need housekeeping for the information processing activities as well.
Right. Let's take a look.
We began with an order entry process where the order was called in on fax end, entered into our mainframe. Mainframe would generate the shipping paper and the documentation necessary to pick material and issue an order to the shop floor for the shop floor to begin the manufacturing process. The overall cycle of that was about 3 to 4 days. It currently takes us 15 minutes or less to do the same process. And we just shortcut, in effect, the computer system by having, when the order comes in, a copy of it is delivered directly to manufacturing. And a parallel activity occurs. Since all the material is available to build the product at point of use, the actual customer order becomes a document that drives a factory. We've learned many things from this particular experiment. One of the key lessons is a lesson about automation and the impact of computer integrated manufacturing, if you will. In this particular application, we've learned that we have to disconnect the computer system from our process for a period of time and let the process drive what we're doing. From that, we can step back and really look at what value the computer system can add to the process. Instead of designing a process around the computer system, we're deriving the process system first, the process of manufacturing first, and we'll automate the information part of that as and when needed.
As this case indicates, if the data collected does not trigger an action on time, such information may have little value, if not a negative value.
Oh, I see.
In fact, just as you have mentioned the housekeeping of information, we can draw an analogy between the office and the factory. Instead of physical inventory in the factory, we have information inventory in the form of paper or data stored in the computer in the office. Instead of material flow, we have information flow. If we think about this, we'll find that the same principle we are studying here will equally apply to order taking, invoicing, and many other information processing activities.
Do you have an example?
Sure. These pictures here show an example of the engineering change process at Aishin Siki. As you see here, this is one-piece flow layout. The yellow line and the awareness table indicate good housekeeping and visual control is practiced here. From the simple improvement, work which used to take 10 days to process is now finished in less than an hour.
Boy, that is surprising. I'm beginning to see the real power of these techniques.
Again, though, people's involvement is the key to implement these ideas successfully. And as you can tell, all of these techniques are meaningful only when people understand their significance and then practice them with certain discipline.
And for that to happen, we need to first share these ideas and then educate ourselves.
Right.
Those improvements have to continue to be done each and every day. It is nice to relax in an office, but it's much more important to be out there on the work floor and manage by seeing the visual evidence of the operation. Visual control is one of the best tools that I found in the total production system.
Previously, we have learned that poka-yoke, or fail-safe mechanisms, can eliminate defects at the source. This becomes especially important when we are to implement the full production concept. For example, smooth one-piece low production in a U-shaped line cannot be achieved without ensuring quality at the source. However, when simple poka-yoke can't solve the problem, further consideration must be given to improving the process capability so that we can establish a reliable production process and adequate quality control, or QC. The basic principles of QC we should remember are: 1. Our first priority is customer satisfaction. For all the work we do has only one purpose: to satisfy a customer. We must always remember who they are and listen to what they may have to say. 2. Remember that QC starts with individual problem-solving activities. To paraphrase John F. Kennedy, ask not what your company can do for you, ask what you can do for your company. 3. Control must be based on the facts. Investigate the data available and look at each problem firsthand. Don't rely on the emotions or recollections of others. 4. Learn the basic technique of QC. These include histograms, cause and effect diagrams, check sheets, Pareto diagrams, graphs, control charts, and scatter diagrams. These are often referred to as the 7 tools of QC. 5. Use the so-called PDCA cycle of continuous improvement every step of the way. PDCA corresponds to plan, develop a plan. Do, perform work as planned. Check the results for conformance. And action, analyze the results and take action for further improvement. 6. Attack or focus on key areas first. Instead of wasting a lot of effort on things that contribute little to a solution, concentrate your efforts on key areas, using the Pareto principle. 7. Control the factors causing uncertainty or scatter. If you can eliminate the scatter, you only need to suck in on target. And 8. Report progress by sharing your QC story with others. After progress is made, share the results in a standardized form so that more employees can benefit from other people's positive QC experiences. The bottom line is that everybody can be a problem solver. If we need to depend on our inspectors to find all the defects and our engineers to solve all of the problems, then it's already too late and too costly. Furthermore, doing this, in effect, is squandering the capabilities of our people. In principle, we should all agree that quality must be addressed at the source and by those who are closest to problems. In fact, the same concept all applies to the quality of the managerial process. Understandably, if we are to meet our customers' needs, our own managerial processes need to be well under control in all areas of the organization.
This is our hand load line, and these people use statistical quality control to monitor the process quality in their area. This gives them feedback on the process quality so they can take action to improve their own process. And the wall you see behind me is actually the display of process quality and statistical quality control tools for all our process centers. In particular, this is the wave sorter process. You can see here that we have short-term feedback, actually daily feedback on this X bar chart. We move down here and we see Pareto charts, so we can look at long-term trends over a number of weeks, from week 5 to week 23. We're also able to look at defects found internal to the process and defects found at a customer in the next process in the flow of their customer. This is based, the Pareto chart here on a quantity-based, and we also have a parts per million level of XRR chart. This wave sorter process in particular has provided us with a real success story with statistical quality control. A few years ago, we had a quality level of about 20,000 parts per million in this process, and through using statistical quality controls methods, we've been able to achieve an average of 2 parts per million on our wave sorter process. We're not satisfied with that. We keep continuing to work on this process so we can get it down to 0 parts per million.
Now, let's hear from the supervisor in charge of this area.
This chart indicates our customer defects, and in the morning, the R operator collects all the data and plot on the chart. And if we see high peak, obviously we need to work on. And so we take action right away. And also we have ongoing continuous improvement team, which we can resolve this problem as well. So if we find out what caused that, immediately we go tackle that problem and try to solve that.
The Quality Circle program has been an excellent method for operators, lead men, and supervisors to be involved with the problem solving itself. After all, the people on the shop floor are much more familiar with the actual problems than management or people in the engineering group. Tapping that resource has been an excellent method for making improvements at the ABC. These are some of the things that have been finished in the past in the press room. We have problems such as problems with the header board tunnel, or a rear skirt, or some of the other parts that are included within the truck bed. In solving a circle, there's a lot of work that goes into it, and I can give you some examples here. The Pareto analysis, the cause and effect diagrams, following the targets, doing additional studies before and the current situation, and diagrams to show exactly how some of the problems are solved.
So we can all learn the tools for problem solving.
Yes, and once you solve a problem, you may discover just how satisfying such an experience is.
Then is the question of getting used to it?
Yes, for that reason, managers need to be educated so that they themselves can use these tools and teach others. Then, we should support people to learn to use these tools.
Japan's quality circles would be one of these activities, right?
Yes, but one thing we should all understand here is that it was not an easy process for them to develop the skills that they have now.
Well, so what you are saying is that it's not Japanese magic, but that they went through the same evolutionary process, and it was not necessarily an easy process for them either.
You're right, there's no instant pudding. There's a need for management support and encouragement. Also people's interest, pride, ownership. These things are necessary for making it a real success. And for this to happen, the Japanese try different things such as creating the Deming Award, the Japan Quality Control Award, and so on, and publishing numerous magazines such as these, and books such as these. They are all important parts of developing a supportive environment for people to study these techniques and practice them. In fact, if you attend a Deming Award ceremony or any conference on QC or suggestion program, you'll be impressed by the attendees' serious attitude throughout.
Well, it sounds to me like they have tried to develop a supportive environment to learn these skills, almost like a national objective.
Yes, I think you can say that, especially when such activities serve the nation's interest too. The last point I want to make here is that when we learn these techniques, these tools may not only help the organization and company, but perhaps more importantly, these tools can enrich our lives too.
Why is that?
Because the process of problem solving is universal to any environment. If there's a problem, there's always cause and effect relationship. And since we have only limited resources, we have to prioritize or focus our efforts to solve the problem. And that's what we do throughout our lives anyway. Without recognizing it, I think we're going through a plan, do, check, action cycle in our life. That's what I'm saying here.
I see.
Let's see an example of problem solving at FMI. As we have studied line stop concept before, this example shows the use of problem solving techniques to reduce the number of line stops.
We started counting how many times the line stopped and from every station, and that would tell us how many problems we had. And right here we started doing this chart, and process control, it helps us to see how many times the line stopped, and right here tells us which station, how many times every station did stop. It helps us realize what kind of problems we had, what kind of problems we can resolve first, and which problems that we could do at the beginning of the program. The problems that we resolved when we started doing that, the problem that we resolved went down from 493 times, went down to 133. From those kind of problems that we had there, we made a visual drawing, and right here we can see that from every station we have information of those amount of times that every station had to stop. And from that we can tell how many problems that we had. From there we can tell the problems that we had, draw a chart, and see which category that we had to resolve: machine, and method, and material. And once we put it in that category, we start resolving these problems. Okay. And from every station we have those problems drawn in here, and we can start now resolving them.
As our factory becomes more streamlined and inventory levels are reduced, we may still need to address problems associated with machine maintenance. In recent years, several sophisticated computerized maintenance programs have been developed to serve this purpose. However, without combined efforts of the operators, management, maintenance crews, and other support people, effective production maintenance will never be achieved. An especially crucial step in achieving trouble-free operations is the early involvement of the operators. Because they run machines, they have the first opportunity to sense any problems before serious machine breakdowns occur. We need to take advantage of this to address machine maintenance at the source, rather than by collecting the information after the fact. To facilitate this communication at Toyota Auto Body of California, a visual aid was installed to inform maintenance crews about the condition of the machine. So they call this maintenance Kanban. Just as inspecting parts after the defects are produced can never totally eliminate defects, we cannot establish trouble-free operations without addressing the issue at the source. This shows an approach to preventing them. One of the key points here is the realization that people themselves are the cause of the problem. Typically speaking, machines do not create problems by themselves. Rather, people let machines break down, for example, by forgetting to oil, or retighten bolts, or by leaving the machine dirty, or perhaps by not following the proper instructions. As in the case of housekeeping,